This is Herb, replacing David Griffiths for the September 16th lecture. Somehow the recording from years ago didn't come through. Today we're talking about position, velocity, and acceleration, as always, and I'm answering a question that a number of you have posed just out of curiosity, which you'll see in a minute. In the last two lectures, we've been talking about constant acceleration, both for dropping or throwing up in a one-dimensional gravitational field problem, and also for projectiles. Today, I'm returning to the general case. General meaning it's not constant acceleration. If you know the position of an object, xt, then we know you get the velocity by doing the slope of that curve. And that's the velocity. And this process is called differentiation. Take the derivative. Similarly, if you know the velocity as a function of time, you find the slope of that curve, which we write, by the way, as dx dt. You take the slope of that curve, and you get a of t, which is dv dt. And the math process is differentiate. What if we want to go in the other direction, given the acceleration, to find the velocity? And the acceleration is not constant. So you can't use all those formulas and the experience you get from the homework problems. You have to do it in each case from the given function. You'll find that this is very important in mechanics. Given the acceleration, to find the velocity. What we need to do, oh, and of course, given velocity, you can go backwards by whatever that same process is to find the position. That's actually typical because the laws of physics tend, in our class anyway, to give you the acceleration as a function of time. That's what you start with. And you'll have to be able to go from this second derivative of x back to the first derivative back. So in a sense, the answer is quite obvious. What you have to do is undifferentiate whatever you have. You have to find the function that is the antiderivative of the function. That process is called integration. And what we're going to be talking about today is integral calculus, which is pretty much the rest of the analytical math that we need for the entire course. So that's today's subject, the integral calculus, integrating simple functions and how you use it in mechanics. I'm going to give you an example that's pretty easy to start with. Suppose we know that a of t is not constant, but equals 6t in appropriate units. Not only is it not constant, but as you can see, it increases as time goes on. Problem. Find v of t and x of t. How do we do it? Solution. To get v of t, you must have a function that when you differentiate it, it comes to 6t. Because differentiation lowers the power, we know that it would have to be a t squared. Then we use our little heads to see that t squared is going to bring down the 2. So there has to be a 3 here, because otherwise it wouldn't be 6, it would just be 2t squared. So it has to be 3t squared But that's not enough, because this formula, by the way we constructed it, always gives you velocity as 0 at t equals 0. And so a constant, which wouldn't survive when you differentiate it, because the derivative of a constant is 0, and the sum of two terms has a derivative which is the sum of the two derivatives. A constant has a 0 slope, the derivative 0, so that still gives us as the acceleration 6t. So that's the answer. So notice you can always add a constant of integration. That's what we call it when we do this integration. And that's what the name is here. You differentiate to find the slope of the function. You integrate to find the antiderivative, that function which would have been a constant. I mean, would have been the velocity. Can you think of what the function would be to get x in this case? We do the same thing again. V0 is the derivative of V0 times t. 3t squared must be something that involves a 6. I mean, whoops, giving away the answer, a t cubed. So what function will give us the 3 in front? T cubed gives us the t squared, because this is going to go down. But the 3 also comes when you differentiate to become a constant multiplier. So this is right, but again, what have I left out? This function always has x equals 0 when t equals 0. Both of these terms contain at least one power of t. So the right answer is x0 added to that. And you see similarities, but not the same exact formula as the one that we had for constant acceleration. Here's an increasing acceleration, and the terms are slightly different. There is an x0 and a v0t, and it's t cubed is the starting point. Physically, x0 is the starting position, and you always, each time you integrate, you get a constant of integration. This one gave us x0, the previous one gave us v0. If we had started with jerk, we would have had an a0 in our function. If anyone then gives you, for the purpose of the problem, what the starting position and velocity are, you know everything about the problem. Cut. Okay, the geometrical interpretation of the integral is also very interesting, and pretty much the rest of this lecture will be about integration and the integral calculus. It turns out, we'll go to the other board in a minute, that the geometry is quite interesting. Here's an arbitrary curve of v versus t, and x of t will relate to the area under this curve. The diagram here we'll come to in a minute. Let's do an easy case over there. Remind you, differentiation for geometry gave the slope of the curve. V of t is the slope of the curve x of t at each point. X, going backwards, turns out to be the area under the graph of v of t. And I'll show you that in easy stages, I hope. Let's take the simplest possible case. The velocity is constant. So I draw the graph, v versus t. A constant is a straight line. And the area on the graph, delta x, between the times t1 and t2, which is delta t, is the velocity, here there's no function, times delta t. That's from the definition of velocity. If velocity is constant, then x keeps increasing at that rate. For example, let's say 1 hour at 20 miles per hour would be 20 miles. So that's the shaded rectangle under this quote-unquote curve. What if the velocity is not constant, which is what I talked about first? Then the trick that makes the integral calculus is there's a little bit not quite right if we take the velocity v of ti and we add the tiny rectangle here for a small delta t. The velocity is approximately constant, and that case holds. But the rectangles that you have to add up are all very different. Conceptually, you chop up every single area that you're interested in. How far did it go between T1 and T2? You have to add all these areas because we know that each little area would work like that constant on the other board, and add them together. The ith piece, 15th or the 18,000th or 2 millionth piece, is the area of the little rectangle with the small delta t in it. If you add them up, and you can see that it's still a rectangle, and a rectangle has an area that's the velocity at that particular point times the time that the increment of time that elapses. Evidently, the distance traveled is still the area under this curve, but you get it by adding millions and millions of the little tiny rectangles. It's not quite exactly right because you see there are these nicks and pieces here. If I use that as VI, I'd have a little extra. And there are places where you'd have a little less, and there's some places where the rectangle is a pretty good approximation. But I think it's clear that if you chop the interval into skinnier and skinnier pieces, for ordinary smooth functions, the contribution of the leftover little pieces, where it's sloping up or sloping down, becomes smaller and smaller. And what we really want are the limits of infinitely many infinitesimal narrow pieces. So you want the limit of the sum of all of these pieces. Probably should use different. From T1 to T2. And there'll be a notation that we'll get to that some of you may have seen before in calculus. Let's give an example that you already know. I think I have room over here if I can get to it. The wastebasket's interesting to have in case one of these markers craps out. Let's do constant acceleration. Constant acceleration, v is equal to v0 plus a times t. It's a nice straight line. Easy thing to do is to start at v0 and end at t. We'll draw it nicely with the positive acceleration. This is the curve of v versus t. This is the time t. I think you're going to like this result. And here we have v0 starting at 0 and t. So we break it up into two things whose area we can calculate, v0 times t, and the triangle. If this is v0 and the velocity is that at time t, then this area is a times t. I mean, this height is a times t. Now this is going to be a nice little calculation. The area consists of two parts. The triangle here and the rectangle there. So the area, which we say is going to be x of t, is rectangle v0 times t plus a triangle whose base is t. See, it's the same as this. And whose height is at. And the formula is 1/2 height times base. We get x of t equals v0 t plus 1/2 at squared. A formula that I think should be quite familiar. And on the lecture where Griffiths talked about it the first time, he guessed that that was what the answer is. This is actually a derivation that shows you it's right. going from the curve to the, for velocity to the actual value, which we could plot as the curve for x of t. Okay. This is sort of a systematic establishment of the, all of the formulas for constant acceleration. Okay, but wait. What I've really calculated here shouldn't be called x of t, because it's really the distance traveled in the time t. And I could have started at x equals x0. This is only x of t, as I wrote here, if I had started at t equals 0. So really the final answer is that x of t equals x0 plus v0t plus 1/2 at squared. And that's an illustration of an important point, that whenever you do an integral, whenever you do the area under the curve, it's possible to add a constant of integration, in this case x0. Now we have exactly the same formula as we studied for constant acceleration. That makes sense because the graph we used is the graph for constant acceleration. I'm going to try to do it in general. So hold on a second while I move to the other board. Okay, so now we want to get the general notation and terminology for this whole idea that I kind of foreshadowed on this blackboard before, of defining the area as the sum of 1,000,000 billion little tiny rectangles in the limit where they go to 0. It suggests the following notation, that the area is defined as approximately V1 times delta T1, first level area, plus V2 times delta T2, plus etc., all the way up until we get to as many as we've divided into. There's a mathematical notation you may be familiar with for such a long sum, and that sum is indicated by a sigma, and then we can have each of the terms with just an index. Let me repeat exactly those terms. V sub I times delta Ti, summed from 1 up to the number n that we've divided this whole area into, whatever the shape of the curve is on top. This is a capital Greek letter sigma, which is their version of an S. Only to be exact, instead of this, which means approximately equal, we want the limit as each delta t becomes 0, and every biggest one becomes 0 of vi delta ti. Oh yes, so in order to get each one to become smaller and smaller, we want the limit as delta t goes to 0 for every one of them, and as the number of pieces becomes infinite, and goes to infinity. Now there's a notation that if you've had a little more calculus, you are quite familiar with, and it's kind of a hybrid between Greek and Latin, both languages well known to the people who did this, and that is that the area is denoted as the integral. This is a distorted S for sum of V, and as we did before in derivatives, dt instead of delta t. So this implies the stuff about the limit. The area equals the limit of the sum, which is denoted as the integral from t1 to t2 of v dt. There's the graph. You're starting at t1. You want the area under the whole curve. You can do it as a limit of a giant sum of tiny rectangles. It applies to any graph as written here. The one we're most interested in is the generalization of this graph I'm erasing, that x at t2 minus x at t1. The distance added by doing this velocity is the integral of v dt, the area under the curve of velocity from t1 to t2. That's the complete notation for the definite integral. And correspondingly, of course, the same thing holds for the relationship between velocity and acceleration. V of t2 minus v of t1 is the area under the curve for acceleration as a function of time. So that's what we call it, the integral of v for x. And to go from a of t, you do the integral of a to get v, then you do the integral of v. But how do we actually calculate it? Let me do an example similar to the one that we had on the whiteboard, so I'll go back there. Just do one example, so I'll start with v. Suppose v of t itself is equal to t cubed. Then the antiderivative, the function that gives this as its derivative, will be x. X equals t fourth over 4. How did I get it? We know to get t cubed, you have to be at t4 because I'm going to reduce the power. But if I just had t4, I wouldn't get t cubed. I have to divide by 4 so that when I bring down the 4 to do the derivative, I get 4t lower the power to 3 divided by 4 equals t cubed. You can always check your indefinite integrals by doing the derivative, but that isn't quite right because when you start with a function and you integrate to get the answer, there's a constant of integration that can be added. It wouldn't change this next step, the derivative, so we know we still have the right answer. An antiderivative like this, going from the slope to the curve itself, always contains an arbitrary constant. In this case, the final answer is x has to equal t fourth over 4 plus, can you guess? At t equals 0, this term would be 0, so it's x0. That's very much implicit in the notation. Let's put it all together now. I think the whiteboard might be easier to see. What we found is that there are actually two different ways, and I've emphasized that all through in doing the calculus, of interpreting and understanding what the process is. In this case, integration. So when we put that all together, we end up with given v of t, to find x of t. Those two methods are to plot, I'm writing it right in the right place over the word geometry, plot v of t and find the area under the curve. That's the geometric interpretation, and the area under the curve, as we've seen, is the distance traveled, which will be the difference between the starting and the final x. And the other is, that's geometry. The other is more the algebraic or analytic method. Find the antiderivative function of v of t, which is a function which if you were to differentiate this and find this derivative, you get back to the antiderivative. Put it in quotes. The combination of these two methods is called the fundamental theorem of calculus. This is our punchline from a mathematical point of view. To determine the area under the curve, which is called the definite integral, find the antiderivative. Anyone will do. You can think up a function whose derivative is the curve. And subtract, in this case it would be x of t if that's v of t, and subtract the values of x of t at the endpoints. So any curve v of t, if you knew x of t, the area under the curve here would be area equals x at t1 minus x at t2. And if the battery survives on the camera, I'll give you one last example on this other board. I think it shows up better when you use the whiteboard for video. Find the area under the parabola v equals t squared, v of t equals t squared, between t equals 1 and t equals 2. Solution. According to the fundamental theorem, the integral of t squared dt from 1 to 2 is equal to t cubed over 3. That's a function that would give this derivative, plus a constant evaluated between the value of t equals 1 and t equals 2. This is the notation, sometimes written just with a straight line, 1 to 2, which means take the end point, the top, and evaluate your function, and the starting point, the bottom number, and subtract it. First evaluate at 2, then subtract the value when t equals 1. So let's do that. At 2, we have t cubed. 2 squared is 4, 2 cubed is 8, so that's 8/3 plus the constant. That's the first term for the upper, and you subtract the value at 1. Easier for me anyway to calculate. 1 cubed is 1. Notice this gives you 8/3 minus 1/3, and always gives you plus c minus c. When you do the definite integral, the constant that appears in the indefinite integral always cancels out, and this gives us 7/3 So the area under the curve here, if I drew this correctly as just the function t squared, where this would be the value 8 and this the value 1, the area under that curve is 7/3. We'll end right here, pick up in the next lecture.